Hello, this is Dr. Strickland. In this video, we're going to finish our investigation of organometallic catalysts involving palladium, and then take a look at the catalysts involving ruthenium, molybdenum, or tungsten. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we'll do together in class. So we talked about the Suzuki reaction, and now we've got the Heck reaction, which is kind of the counterpart. It involves a palladium catalyst with a couple of ligands attached. And remember, the L stands for ligand, which could be a variety of small molecules or anions. And so it's the same kind of coupling reaction, but instead of having an alkyl borane, what we've got is a monosubstituted alkene. And back in the general reaction pattern, it looked like this. And this Z group is generally either bulky or an electron withdrawing group or both. And you can see that in this case, it's this ester with the partially positive carbon directly bonded to the alkene. So this is an electron withdrawing group. Okay, so in a Heck reaction, the two atoms that are going to join are the one that's bonded to the halogen in your vinylic or aryl halide, and then this carbon right here, not the one that your substituent is attached to, but the other one, and it will attach trans to the Z group every time. So in this case, so this is the carbon from the halogen, and it's bonded. The new bond forms exactly where the old bond was. And so we've got this and this. Okay. And so the new bond I'll say new bond is trans to the substituent from the alkene. And this stereochemistry from our vinylic halide, stereochemistry is retained, whatever it was. If it was trans, it's retained. If it was syn, it's retained. But the new one, this new bond here, is formed trans to whatever this substituent is, okay? So just keep track of your pieces. Half of chemistry is staying organized. Okay, so when the Heck reaction involves a vinylic halide, stereochemistry of the carbon-carbon double bond vinylic halide is retained, and the terminal carbon of the alkene reactant takes the exact position of the halogen. Okay, so same story, but this is a cis instead of a trans, and sometimes I think the trans is easier to see. So we're joining there and here. Okay, so this carbon and this carbon. So I want you to pause the video, draw the product, and come on back. All right, welcome back. So I'm going to start with the alkyl halide because I know that this new bond is going to take the place of the bromine exactly. So if this is cis, that's going to be cis, right? This is, and this is cis. Now, the new bond this one is for the one that's formed right here has to be trans to your substituent. So this one has to be trans. Always. Okay, does that make sense? Okay, so this is the carbon from the vinylic halide. This is the carbon from your monosubstituted alkene. So with Heck reactions, I think one of the big things is keeping up with stereochemistry. So practice. That's the way to get comfortable with that. So the organometallic catalysts involved in ruthenium, molybdenum, or tungsten are involved in a special kind of coupling reactions that are called metathesis reactions, excuse me. And so if you've got two alkenes involved, it's called alkene metathesis. And if you've got two alkynes involved, it's called alkyne metathesis. And so they have similar catalysts, but not identical. So these guys are the two alkenes that are involved. And generally speaking, at least with the ones that we're going to do, the two starting compounds will be identical. And so what you find is that you start with two alkenes, you end with two alkenes. But what you're doing in the mechanism is breaking the two original carbon-carbon double bonds, and then the pieces are reassembled. But if you line them up like this, it's easy to see where the assembly goes, because these are the two pink ones, and these are the two blue ones. And sometimes people like to do it like this. So you could, at least initially, do your two products like this. Okay, so again, the two pink ones and the two blue ones. Okay, so, and either way is fine. You know, you can draw your products like this, you can draw your products like that. For me, perfectly fine either way. So when they get a little fancier, then you just gotta see where the carbons are that are going to be bonded in the products. So if we line them up identically, and this is an intermolecular reaction because the alkenes are in two different molecules. You can see that that's going to be different from the one over here. This is an intramolecular, but it's the same kind of thing. It involves two alkenes. It's just that they are both in the same molecule. All right, so I want you to draw the products for this one. Pause the video, draw the products for this reaction, and then come on back. All right, welcome back. So I think I'm going to do mine vertically this time. So the pink ones and then the blue ones. I think I am going to do my methyl groups this way. Do that to emphasize the carbon-carbon bonds between the methyl groups and those vinylic carbons. These are the pink ones. These are the blue ones. Okay, so here you can see that with this intramolecular reaction, we're going to form a six-membered ring. And it's going to have not just a single bond, but also it's going to have a double bond. So the benzene ring is just along for the ride. And then this is, again, ethene. You can see that ethene is often a product, and the reason for that is because ethene is a gas. And if you can have your gas just come out of solution, then you can drive your equilibrium to the right and increase your yield. Okay, so if you want to do alkene metathesis, you need a Grubbs catalyst, which involves organoruthenium compounds. So if you want to do the same kind of reaction, but with alkynes, what you need are Schrock catalysts, and Schrock catalysts involve molybdenum or tungsten. So with all of these catalysts for the metathesis reactions, I'm going to ask you to know the name of the catalyst and the metal that's involved, and nothing more than that. Okay, so similar reaction. We're going to take two alkynes now and do the very same kind of reaction where you break the triple bonds that are there and then reassemble them so that now they're attached to each other, the pink to the pink, the blue to the blue. All right, so I'd like you to pause the video, draw the structure of these compounds that result from this metathesis reaction, and then come on back. All right, welcome back. So those two and those two, and you don't have to color code anything. I just think it's a good way to stay organized. And so you can draw the products like this. You can stack them, or this time, I'm going to do them like this. And here are the pink ones. And here are the blue ones. A good idea to make sure you can name all these alkenes and alkynes just to keep your nomenclature skills sharp. All right. And so the common name for this guy, and this is ethyne, of course, common name is acetylene. So any welding that's done generally involves acetylene torches, which uses a mixture of acetylene and oxygen gas as the fuel. All right, so that is the main story on organometallic catalysts involving ruthenium, molybdenum, and tungsten, and what we did with the Heck reaction. If you have any other questions, please send them to me.